Ladies and gentlemen, hello, hello. Am I coming in loud and clear? Let me know in the chat, people. Can you hear me out there? Hello, Wei Lin. Good to hear from you and everybody else. Welcome. So I've asked everybody on the polling, how was lab test 2? Well, most people said it was great. Some people said it was okay, and some people haven't has said I haven't done it yet. So whatever it is, I hope you're doing okay. And is it really week 9? Like seriously, is it really week 9? Can't believe it. Anyway, so that means next week is our final week. It's going to be very sad, very sad. All right, well, thank you for joining me today. We're going to continue with our look at improper integrals, okay? So I just wanted to clear up something from last lecture. At the end of last lecture, Tom stayed behind and said, look, Chris, what's going on with this example, okay? And I had a plus there, and it should have been a minus sign. But let me just refresh your memory, okay? I'll fix it up now. We want to know if these types of integrals are finite or not, okay? If they converge or not, I guess, really. And when we apply a comparison test, we're essentially, comparing one integral with another. Okay, now because this is greater than or equal to this on this interval, we can say this this is true. Now the problem, but this is helpful because this integral on the left-hand side is a divergent P integral. Yeah. Okay, so that goes off to positive infinity, and because of that, this must diverge. Right? Okay, so the point I was trying to make with this one, and make sure you change the minus to a plus, is, okay, well, we can do something similar here. We can say, oh, right, that is greater than or equal to that. Now, the problem here is that converges. All right, it's a convergent P integral because P equals 2. So that's finite. It says nothing about this integral. Okay, so this is a convergent P integral. But it says nothing about this integral. Integral. Okay. So this inequality says nothing about this integral. It's not helpful. That's the point I was trying to say on Monday. And I didn't really make it very nice because there was a plus sign there. Okay. So what we need is more tests. Okay. But let me just ask you a question. In that final example, do you think the integral converges or diverges? So let me go back to the document camera. If you had to take a guess, do you think this integral converges or diverges? So is it, is there a finite amount of area? Yeah, Nicholas and Russell, it definitely converges. You can kind of see that because if I cover up the constant, then I get a convergent P integral, okay? So Absolutely, right? So it's p equals 2. So even though we can't apply this comparison test, maybe we can do other things. All right? So today's lecture is a little bit more about these improper integrals. And we're going to talk about a special test that involves limits. Okay? Oh, yeah, great. Can't wait. All right? So the most important thing from this is LFCT, the limit form of the comparison test. Okay, and lastly, at the very end, we're going to change the subject and just talk about functions and integrals. Okay, so these things are all about convergence or divergence, and this is really something slightly different. Okay, all right. So this is really important, the limit form of the comparison test. Okay, you can abbreviate it to LFCT. Okay, all right. So let's look at the assumptions. The idea involves a limit. Suppose you have f and g being non-negative bounded functions, so kind of similar to the functions that we're already looking at. And suppose there is a finite number, positive number L, such that this limit is a finite number, right? So this is, okay. Then what the limit form of the comparison test says is that both of these integrals either converge or diverge. Okay. So what tends to happen is you're given something like this. You have to come up with a second function that you know converges or diverges. And then based on this, you can make a conclusion about your original integral. Okay, so the best way to understand how to use this test is just to look at examples. Okay, so let me have a look at an example for you right now. Okay, because I think that's where that's how people learn really. Okay, so let me see if I can squish one in here. Okay, so suppose I had this integral. Okay, now what I can do, and I'll show you a strategy for this in a minute, I'm going to compare that with 1 on x squared, the integral of that. Oh, actually, let me change that. Let me change that to a 2, just so it's a bit nicer. Okay, so I'm going to compare that with 1 on x squared. Okay, so let f of x equal this, and choose g of x to be this. Now the integral of this converges because it's a p series with p equals 2. Okay, let's have a look at this. So the f over the g is going to be that divided by that. So if I simplify that, I'll get this. Now, who can tell me what is the value of this limit as x approaches positive infinity? Who can tell me? On the chat. What is the limit of this bottom line? It is 1, Nick. Now, 1 is a finite number. And it's positive, right? Now, the integral for this one converges, and what this says is the original integral must therefore converge, okay? So let me just add something here. Since since our chosen integral converges, I converges by the limit form of the comparison test. I've just squeezed it in there. I hope you can read it okay. Stop that girl. Okay, so let me just go through that again. You're given some sort of integral. You have to choose a second integral, and you know that it converges or diverges. And then you look at the limit. If the limit's finite, then the second integral and the first integral, they have the same behavior. Okay? I'm just trying to get my dog away here. Go away, dog. All right, so that's the idea. So let's have a look at another example. And if anybody has questions, feel free to put them in the chat. There aren't many people here today. There's only, 40 people. So if people want to ask questions, of course, there's plenty of time for that. Okay. So you can't solve this using a basic comparison test with, say, 1 on x squared. So this does stuff that the original test can't, the comparison test can't do. Okay. All right. So you'll see in this one, we compared it with a p integral. Remember, p integrals are great because they're easy to deal with and they're very simple. Okay. So remember, an integral like this converges, right? Because 3, let's make this 13, because 3 is greater than 1. An integral like this diverges because the power p is less than or equal to 1. Okay, so these things are super important, not just for comparison test, but also for this limit form of the comparison test. Yeah, Eloisa, there is a strategy, okay, and I'll show you what it is in a minute. Okay, so it's like a strategy, and you can use it when you think it's important or relevant. Okay, okay. So let's get to a more difficult example, and we can talk about the strategy, right? So you can see here, what's the highest power in the numerator? It's power 3. And what's the highest power in the denominator? Power 4. Now, what I like to do is to look at the difference between that. Okay, so 4 minus 3 will give you 1, right? And you compare it with something like that, where the power is here. So x to the power 1. Okay, so look for the difference between this and this, and you can choose, in many cases, you can choose your g of x to be a p function, where p is the difference between this and this. Okay, so let me just show you the previous example. The highest power down here is 2. The highest power up here is 0. 2 minus 0 is 2, so that's why I chose 1 on x to the 2. Eloisa, is that starting to make a little bit of sense? Let me know if I need to talk about that strategy a bit more. Okay. So look at the difference between the highest power down there and the highest power up there. Okay, so who can tell me, let's call that, I don't know, I. Does the integral of this function converge or diverge? Russell, yes, you rule. So let's consider it diverges. Okay, a divergent P integral. So then let's look at the limit of this over this, okay? Okay, so it's going to be a little bit messy. So we're going to get this. Okay, so the 1 on x can come up here, and then you can take the limit. Who can tell me what is the limit of this giant mess going to be, right? Who can tell me on the chat? Well, let's have a look, Russell. It's not going to be very helpful if it's undefined, because we can't use the limit form. So as x goes to infinity, what is this going to? Joyce is right, okay? So this equals 4, because the dominant terms, x to the power 4, you can divide and you'll get 4. Now, this is a finite number, of course, and we know this diverges. This is a finite number, so applying the limit form of the comparison test. Now, well, does it converge or diverge? Our new integral diverges, and therefore the original integral must also diverge. Okay? So that's it. I mean, and also you can kind of sort of guess, these terms are not going to affect it very much compared to that. And there's a difference in 1, same with that one, okay? So this looks kind of like 1 on x anyway, which diverges. Okay, so now it's time for questions. If people want to ask a question or put something in the chat, or if they want me to explain something a bit more, then just let me know, because we've got plenty of time here. Yeah, sounds good. Yeah, Abdulaziz, look for the difference between the highest power in the denominator and the highest power in the numerator. Okay, so 4 minus 3 is 1. Choose a p function that has the p-value difference between the two highest powers. Does that make sense, Abdulaziz? Is that sinking in now? Mm-hmm. So that's the way I look at it. That's the way I try to do it. Okay. All right. Now this one's a little bit more difficult. Before we actually do this, I want people to have a guess, right? So I'm just putting something up. Have a guess. Have a look at the integral. Does the integral converge? Yes or no? What do you think? Based on any kind of ideas you might have, or not. Keep those responses coming, people. So some people are saying yes, some people are saying no. If you don't know, just guess, right? Just have a guess. It either converges or diverges. It can't do both. So go on, have a go. It's week 9. Next term, you might not be able to do this sort of stuff. So you may as well have a go now. All right, so quite a few people have said, yes, it does converge, and some people have said, no, it doesn't converge. All right, so let's have a look. Probably the most difficult thing here is the square root sign. Okay, that's kind of what complicates things here. Okay, so if I cover up the -1, because that's not going to affect the integral much for large values of x, the root and the power 4 are going to cancel out. Okay, and you'll be left with something like x squared. Okay, so if I was choosing another function, I would say, right, the constant, who cares about the constant? The square root and the power 4 are going to simplify to power 2. Okay, so I would choose g of x to be that. Okay, the highest power in the numerator is x to the power 0. The highest power in the denominator is essentially x squared. Okay, because the power 4 and the square root sign cancel each other out in some sense. Okay, so let's have a look. Yep. So does this new integral converge or diverge? Who can tell me in the chat? Who can tell me? Does this converge or diverge? Yes, Nicholas and Eloisa. It's a convergent P integral because the value of the power is greater than 1. Right? Oh, greater than 1. Okay. So we know that if this limit is finite, right? If we take this and work out this limit and it's finite, whatever this does, this has also got to do. Okay. So if I just call that, say, I. So let's consider the following limit. All right. So this will be our G, and this will be our F. Okay. So F over G is going to be a bit of a mess. But I can rearrange it to get something like this. Okay. And so now what is the value of this limit going to be? Well, I can divide the top by x squared and the bottom by x squared, right? So if I wanted to do that, I would get something like this. You don't have to put in this step, but that's what I'm going to do. Okay. So basically I've just divided the top by x squared, the bottom by x squared, and moved the x squared into the square root sign. So you get an x to the power 4. So what is this limit, people? Who can tell me? What is the limit equal to? 6. Yes, it's not a trick question. Okay, so it's finite by the limit form of the comparison test. Whatever this integral does, the original integral must also do. Abdurrahman, how could it be -6? What makes you think it could be -6? It's an interesting question. So here we just, first of all, x is positive, right? Yeah, so from here to here, x is positive, so this thing has to be positive. We're not talking about the positive or negative square root, right? We're just talking about the positive square root here. Okay, by the limit form of the comparison test, since, let's call this J or something. J converges, we must have I convergent or converging, right? So yeah, what a lot of students find difficult with these problems is they don't know whether they're trying to show that it converges or diverges, okay? And you can see the question, does the following improper integral converge or diverge? At the start of the question, you don't know, right? So you have to look at the integral and go, am I going to try to show that it converges, or am I going to try to show that it diverges? So you need to make a decision, right? And if you get stuck or if it doesn't work, then you need to go back and make a different choice for your g function. Okay? So, you know, this will only do one thing. It'll either converge or diverge, right? So if I tried to show that it diverged, well, I would not be able to get it to work, and I have to go back and make a different choice for my g. Okay, but for me the best way of choosing the g is to look for the highest power there and the highest power there, and then look at the difference. Okay, so questions. That's pretty much convergence and divergence of improper integrals. Okay, so what questions do you have for me? What things could be made clearer? Let me know. Let me know on the chat. I might just yeah, I think people can share video if they want to. If they want to ask a question, I've just enabled that. So if people have any questions, it's probably the right time to ask now about convergence and divergence. Two tests, comparison test, limit form of the comparison test. Now, the reason that the comparison test is easy to sort of understand what's going on. With the limit form, it's a little bit more difficult, right? So, you know, why does this actually work? Well, there is a long proof in your class, in your course pack. And I mean, I'm not going to talk about it now, but you know, if you want the details, you can go and find them there. Okay. All right. Okay. So I want to, maybe I'm just going to actually get another piece of paper here. I want to try a little game. We've got a few minutes here before we move on to the integral parts. Okay. So let's play a game. Okay, there's 40 people here. Okay. Does it converge or does it diverge? And why? If you were given this, who can tell me on the chat? Or, okay, a few people are saying it converges. And how would you justify it? If you're saying that it converges, how would you justify it? What would you write? Yeah, it's a p-test, right? So it's a convergent p-test where the power is greater than 1. All right, what about this one, people? Does this one converge or diverge? And why? So a few people are saying diverge. Nathaniel's very done well there with the chat, diverge. So the power P is less than or equal to 1. What about this one? Does that converge or does that diverge? The third one. Definitely diverges. Does it matter that this is a big number? Absolutely not. Okay. All right, let's do a couple more. I'm going to make them harder now. Okay, does this converge or diverge? And if what test would you use to show that this actually converged if you're saying it converged? So if I cover up that, it looks like a P integral, doesn't it? But strictly speaking, we definitely want another test. So my intuition is like, cover that up. It's a convergent P integral. But if I formally wanted to do it, yeah, Nathaniel again is coming through with the goods on the chat. For this one, I would use the limit form of the comparison test. Okay. So these are all P integrals, right? Okay. So for that one, I would use the limit form of the comparison test. What about this one? Do you think it converges or diverges? Okay, Steve says converge. So do a few other people. And what test might you use to show that it actually converges? Yeah, you probably could use the limit form of the comparison test there. Yep. What's another test you could use? The comparison test is fine, Steve. Yep. Is there another? So you probably could use a comparison test. You could probably use the limit form of the comparison test. What other ways could you use? Well, it's not, Russell, good idea. It's not strictly speaking a P integral because it doesn't look like this. Can you see how we've got an extra constant? But there is another way you could do this integral. What's another way you could do it? So we've got comparison test, limit form of the comparison test. What's another strategy for seeing whether this is finite or not? P-test is not okay for this, Javanka, but that's a good suggestion. What other methods do we know? What other methods? Come on, there's 40 people here. These are two. There's a third one that I'm thinking about. It's not a p-test. Well, maybe you can just integrate it straight out, right? Using tan inverse. Okay. So you can actually just integrate via tan inverse. It's slow, and I wouldn't suggest it, but it's a possibility. Okay. So I guess four main things. You can do the integral if possible. You can apply a p-test. You can do a comparison test, and you can do the limit form of the comparison test. So four options for you. Okay. All right, let's get back to the program. Bump, bump, bump. All right, so goodbye, improper integrals. The final part of today's lecture is about functions defined via integrals. Okay, so there are some functions, they're so important, or some integrals that are so important, we actually give them a name. Okay, and I think like a lot of stuff in this course, some of this stuff we're going to talk about will be familiar to you. Okay, so back at school, you might have remembered the natural logarithm function. Okay, so you can sort of talk about it with this lnx, so natural log, or this log to base e of x. Okay, but have you ever seen the logarithm function defined as an integral? Okay, so for this definition, we're actually defining this function via this integral for x greater than 0. Okay, so for x greater than 0, for each value, that kind of defines this natural logarithm function. Okay, so what if we put in, say, x equals 2, right? This is the value of the natural logarithm of 2. So what does that mean? Well, I've got my function. I can draw the graph of 1 on t. Oh, it's not a very good. Let me just move that over here. Okay, I know that the Riemann integral is the area under a curve. Okay, so the area of that region is equivalent to this integral, and that's how we kind of defining logarithm of 2, right? If we went out to 3 and 4 and 5 and 6, then you would get natural log of 3, natural log of 4, natural log of 5. So, you know, this definition has a really nice physical representation through area. Okay, all this is saying is, well, I can go out to I can start at 1, I can go out to any point x, and the area under the curve is what I'm talking about. Okay, so this is kind of cool because it gives us a different way of looking at the logarithm function that kind of makes sense in terms of our integration and work with integrals and Riemann integrals in particular. Okay. All right, so what can we do with our logarithm function defined in this way? Well, I'm glad you asked. There are a whole bunch of interesting properties that you would suggest and expect. Again, you've probably seen this stuff at school, right? So you probably know this already, but let me just show how you can connect the ideas from the previous definition. Okay, so if I want to, that's my logarithm function. If I want to differentiate an integral, the fundamental theorem of calculus says that the derivative and the integral sign disappear, and you substitute this value in here, or this variable. Okay, so there it is. How good is that? You can also see that if I put in x equals 1 here, I'm integrating from 1 to 1. And so you can think of that, oh, well, the natural log of 1 is 0 because it's 0 area. And you have some other properties too, the normal properties that you would expect from logarithms. Okay, so let's have a look at some examples, and then we can finish up. Okay, all right. So two ways to solve this problem. We want to differentiate the function of a function. Oh, actually, that's not right. That's better. Okay. So who can tell me what kind of strategies might we use here? Product rule is an interesting idea. Russell, maybe chain rule? Okay. So I'll do it two ways. So yeah, Steve. So Steve has mentioned what do you do for x less than 1? Well, it's negative of this, right? Because, you know, if you have x1, that equals the negative 1 to x. So that covers it, Steve. Okay, when x is between 0 and 1, that tells us. So pretty cool, huh? Good question. So I can choose, say, u to be sine x. And I know that if I differentiate that, the derivative of sine x is cosine x. Oh, hang on a second. My dog is just eating something. All right, I'm back. Okay, so let's get back to it. So let's apply the chain rule. Okay, so the chain rule says that we can replace this with this. So this is a u here. Okay, so du dx is that. d du of log u is going to be 1 on u. And what we can do is get back to our original x's by replacing u with sine x. Okay, so if you wanted to simplify this even further, it's cot x. Okay, now another way to do this is just to differentiate. You wouldn't do this normally, I don't think you would anyway, is to just differentiate. So alternatively, you could differentiate this. Okay, so all I've done there is I've taken my definition, my integral definition of the log function, natural log function, I've replaced x with sine of x. Okay, so you get something like this, and now it's just a little game of applying the fundamental theorem of calculus using the chain rule, right? So this one's more direct. I would recommend this. This one, it's nice to know, but I wouldn't recommend it. So the derivative of this comes to the front, and then you differentiate this and replace it with that. Cot x. There you go. So that's two ways of doing this thing. This uses the example using the integral definition, and this one just straight out uses the chain rule. I think the first one's easier than the second, but you know, that's just my personal preference. Okay. All right. So you probably know this already, but it doesn't hurt to say it again. If I'm differentiating the logarithm of a function, then it's just the derivative divided by the function. Okay. So that you can prove that using the chain rule, but this is kind of nice for integration. So what you can do is integrate both sides and you know, put your constant of integration in, and the absolute value signs here. You know, you definitely want the thing to be well defined, right? So you can't take the natural logarithm of a negative expression. Okay, so if I was doing a problem like this one, and this is the last problem we'll look at today, what I would see is, well, the bottom, if you differentiate it, is almost the top, right? So what I can do is write it like this. Okay, and so now you can see, well, the top is exactly the derivative of the bottom, right? So, yep. Okay, so you may think, well, why didn't you put the absolute value signs in there? Does anybody know why don't I need the absolute value signs for this particular example? Who can tell me? Why don't I need to put absolute value in there? Yeah, Aiden, you're right. This thing is always positive, so you don't need the absolute values. Yes. Thank you, Farhan and Aiden. So there you go, people. That's a little bit about limit form of comparison test and functions that are defined via integrals. So has anybody seen that definition of the logarithm function before? So if I just put that up again, has anybody actually seen this definition before? Like maybe at school or somewhere else. Has anyone seen it? Abdul Rahman, that's impressive, buddy. This is, you know, kind of cool because you're really just relating it with area under a curve, which is excellent, right? Whereas up here at school, you were saying, well, you know, maybe logarithm function is the inverse of the exponential function. Well, that tells you a little bit, but not as much as something like this. Okay. All right, folks. There's a couple of minutes. I'm going to stop recording now, and people can ask questions if you want to. You can come in. So yeah, I'll see you tomorrow. There is a calculus lecture tomorrow, and yeah, thanks for coming along. And I hope you did well in class test too. But I will hang around for a few minutes. Okay. All right, folks. When will the assignment be marked? Abdul Rahman, 2 weeks after the submission date. That's what it says on Moodle. Oh, Aichan, okay, good question. Let me just go back here. Page 6. Let me see if I can find it. Okay, so just bear with me, Aichan. Okay. So the question is, how did I go from here to here? Is that right? So let me grab a piece of paper and I can show you. Okay. So it's just a little bit of algebra, right? So if I wanted to do this, I would say, right, 6x squared divided by x squared over Okay. Oh, hang on. Let me share my screen. Sorry. Okay, so the question is, how did we get from here to here? I think that's the right way, isn't it? So so I divide top by x squared, divide the bottom by x squared. So this is going to be 6, right? And then this one, if I want to get it in here, I'm going to change it to this. Okay, why? Because, okay, so that goes into that once. Dot, 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 dot. Yep, great, I-10. All right, folks, time for me to say goodbye. Have a great week. I'll see you tomorrow. I know, Nicholas. Well, maybe in the future. Oh, Bill, there was just a question about, do we teach any more courses together? Is the dynamic duo getting back together after this course? I hope so. I really enjoyed teaching with Bill. He's one of my favorite guys to work with, and I'm glad you see benefit in it too. So yeah, I'll say goodbye.
Okay, see you later, Chris.